So, welcome all of you. This is the Charles Chamber of Commerce. So, first thing up, I'll let Chuck McShane, give an intro, tell us a little bit about the Chamber, and then we'll hand it over to Davis for everything else.
Okay. Great, well welcome everybody, thanks for coming out. Happy to have you here. I'm Chuck McShane, I'm the Vice President of Business Data and Analytics here at the Chamber of Commerce for the Charlotte area, Charlotte region. We're focused on really attracting businesses to the Charlotte market and helping the businesses that are here grow. So a lot of what I do is focus around sort of traditional economic data analysis. But there's a lot of growth in this space in terms of analytical techniques, analytical tools, and explosion of data. So I'm interested in learning more about what you all do in your jobs and how that drives the Charlotte economy. So welcome, and feel free to reach out anytime after this. Thanks.
By the way, I'm Greg Gunn, for those of you who don't know me. I think I introduced myself to most of you. So this month, we have Davis, who went to our own local UNCC and now has the job that I'm pretty sure everybody in this room wants, working at RStudio, doing cool stuff with Max Kuhn and the rest of the gang. So he's going to tell us a lot about time series, and I'm sure teach us all many things that we did not know.
Thanks for the introduction. Yeah, so I'm Davis Vaughn. I'll be talking about time series and financial analysis in the tidyverse. Quick things at the bottom, the bit.ly link will take you to a GitHub page with like all of this information and everything else you might need to reproduce any of this. You can just Google my name in GitHub if you wanted to find an easy way to get to it, and then there's the Wi-Fi if you need it. Okay, so disclaimer real quick, most of what you're gonna see today is not really like actually a product of RStudio, because I just started like 2.5 weeks ago. So a lot of this is some of my work that I've either authored or co-authored, and then some bits and pieces of what other people have done, and then some of the work that Max has done with his rsample package, if you've ever heard of that one. Beyond that, who am I? So software engineer at RStudio. Again, I'm on the modeling team with Max Kuhn, so that's like the dream job if you've ever heard of one. And then I went to UNC Charlotte. I have a master's in quantitative finance. I was in that field for a little bit, and then kind of realized, like R is really where I belong in building these packages and making tools to, make your life easier. So on the side here are a couple that I've worked on in the past. The most popular one is by far tidyquant, but TiddleTime got popular as well, and I'll talk a little bit about that. Maybe it's what might come next. So. The agenda today is basically package overload. I'll start with tidyquant, and we'll focus on like what it is and what it could be useful for. We'll then go into a new package called tsibble. If you've heard of that, it is time series and tibble together. It's kind of like what is going to happen instead of tibble time. And then we're going to talk about these two packages that work nicely together, rsample and furrr. Rsample is useful for cross-validation techniques, and we'll talk about how that's useful in time series. And then furrr is useful for doing furrr, if you happen to know of that package, in parallel. So to start off with tidyquant, we have to kind of look at the current state of this world. And right now we have XTS and we have tibble. And if you use time series a lot, you're probably pretty familiar with XTS, because that's a lot of the financial infrastructure is built on top of XTS already in terms of R. It's got this native time index support, and it's built on top of matrices, which is both its biggest strength and, in my opinion, its biggest weakness. Because of that, we don't get the attributes of a tibble where you have heterogeneous data. Matrices can only have one data type, so each column is only numeric, or it's only character. In a tibble, you can have one column that's character, that's all of your tickers, and one column that's your prices, and one column that's your dates, and all of that, and everything's separate. That has a lot of benefits in terms of grouped analysis. So you have this just powerful generalized data manipulation in tibbles that I don't think you can get out of XTS, even though it's got these great packages underlying it and built on top of it, like QuantMod, performance analytics, and portfolio analysis. So tidyquant was then built to be a bridge between those two worlds. It's a bridge between XTS and tibble in the fact that you have a tibble, because we work in the tidyverse, at least I do a lot. I want to convert to XTS, apply some kind of time-based function that I know they've already implemented really well, and then convert back to tibble to just get my result in the end and continue on my tidyverse workflow. that might look something like this. In the top, on the first line, we have tqget. All of the tidyquant functions are prefixed with tq. tqget is kind of a wrapper around a lot of different ways to get financial data. In this case, we're just getting the default, which is stock prices, and we're getting Apple stock prices as a very simple example. What's returned from tqget is a tibble. You're not going to see that here, but just trust me. It's a tibble with a date column along with open, high, low, close, adjusted, and volume. We're going to pipe that into tqmutate. I'm kind of assuming you're all generally familiar with most of the tidyverse and the idea of the pipe and whatnot. And tqmutate is a take on mutate that allows you to do something a little bit similar in the fact of we're selecting some column from our data frame before, the adjusted stock prices, and we want to apply some function on it that's specialized to XTS objects. This daily return function came from the quantmod package and allows you to say, okay, I know there's a date column in this tibble, and I know there's an adjusted stock price column in this tibble. Turn that into an XTS object, go ahead and perform the daily return calculation on that, and then pull it all back to a tibble and append that daily return column onto my tibble. So at this point, we now have a tibble with all of the original columns plus this extra daily return column that we got from the daily return function. The nice thing about that is it just takes care of all of it for you, and you don't even have to worry about it. You then just can pipe that to ggplot and use it in the rest of your tidyverse workflow. You do whatever you need to after that, and you get this nice plot in the bottom right. The nice thing about this is that you really just get a lot of functionality for free. You've got these wrappers that encourage the tidyverse workflow, and then you've got this underlying functionality that comes from all of these 5 different packages that have been implemented for you and well tested and everything. And a number of them are highlighted here just to point out some extra functionality. You saw daily return, but there's also things like apply monthly from XTS, which allows you to just apply any function at a monthly periodicity and then get the result back. TTR has a ton of technical trading rules inside of it that have been implemented, well tested, and these you can just use directly through tidyquant. And there's just a couple other rolling functions, but I'll show some of those a little bit later. So what are we missing with this? Well, it's a little bit painful, right? Because you have all this work that's great, but conversion is slow because we have to go from tibble to XTS and back to tibble. And if you have a lot of groups or a lot of really big data frames, this just starts to suck after a while, to be honest. It's a little limited in functionality because we only get what's inside those 5 packages. If you want to extend it to do other things that XTS does, there's really no way to do that right now. And it's also just indirectly using both the tidyverse and XTS. I'd really like it to just be a tidyverse solution if I could. I think that just lends its hands to a lot of powerful speed-ups in my opinion. And then there's just no support for a time-based index on a tibble directly. And that's really the big one that I'm after. So my question that I pose is, wouldn't it be nice to have a tibble that has this time index support that also fully leverages all those tools of the tidyverse rather than having to borrow from XTS, even though it's great and it has its own benefits. This is where tsibble comes into play. We'll move on from tidyquant and we'll go into the tsibble world where it's essentially a TS plus for time series plus tibble becomes tsibble. If any of you are oldies from R, you know the original time series class in R was TS, and that's what they borrowed from. I don't particularly like that name, but we are stuck with it. A little history. So this is where I was going to talk about tibble time. Tibble time, if you happen to see the rstudio conf presentation I gave from this past year, tibble time was my package that essentially does the same thing. It wraps up a tibble, adds the ability to specify a column as your time index, and then gives you all these extra functionality around that to do some kind of time-based analysis in the tidyverse. Tsibble and I have borrowed code back and forth, and eventually we just decided it's best for the R ecosystem if we just did one standard going forward. Tsibble is led by Ira Wang in Australia, along with Rob Hindman. Rob wrote the Forecast R package, if you've heard of that, and it's just massively popular, and he knows exactly what he's doing. He's very into the tidyverse, and I've had a conversation with both of them, and we just decided, like, I'm gonna help you guys out, you guys run with it. They have a team, PhD students, that are already working on that and another extension packages that I just like can't keep up with on my own. So I've been fine in saying, you just guys do your thing, I'll help you out when I can. So with that said, what is a tsibble? Tsibble is an object that consists of an index, a key, and other measured variables that come along with it that's built on top of a tibble. And why is this special? Well, for one thing, it utilizes this extra knowledge now that I've been after. We've got this time index, maybe it's a date column of some kind, and we've got this key. A key is a special thing I haven't talked about yet, but it's essentially a way, like a primary key in SQL. It's a way of saying this is like an identifier that specifies this is a unique row. So in a simple example that I'll show later on, you might have a symbol column where it's like Apple, Facebook, Netflix, Google as your stock, and then you'll have a date column that's maybe daily dates, and Apple 2013-0101 will specify that as like, that's the unique row. The key in that case would be the symbol column, and the index would just be the date column. But a key could consist of multiple columns and whatever you need to get that to be a unique row. The other thing is that this underlying data type is the same. It's still a tibble, and that's really important because we still get to inherit all of those abilities of using functions like dplyr that are really, or packages like dplyr that are really good with data frame manipulation. So how do you create one? Use this coercion function as tsibble is the best way. You'll pass in a data frame, a data of your choosing. You'll specify the key using this ID function. Again, that's useful for when a key has multiple columns that together make up the single key. And then you have an index as well. If you don't pass in that index, it'll automatically try to find one for you and tell you what it's found, but I find it's useful to specify. And then the other columns along with it.
If you have multiple columns making a key, do you just comma separate inside that?
Yeah, so it would be like ID key 1, comma, key 2.
Does it add that as a new column, or?
No, it doesn't even manipulate them. It just like stores them internally as like this thing is the key, and it makes sure that no rows are duplicated within that specification. There's other things you can do that I won't get into in terms of like hierarchical time series of like crossing and nesting structures within your keys. So maybe it's like it's a state, and then you have neighborhoods within your state, and it's like counties, and there's other specifications for ways you can do your key that makes it a little bit more powerful, but that's still being built. So to get into some examples, we're going to need some data. This is some data I showed at the RStudio conf that I really like. It was in San Diego, so I used San Diego's Airbnb bookings. That's out there, this website, you can look at it later. Essentially, it has just a room ID that tells you which room was booked, last modified column to tell you when it was booked, the price of the booking, and then where in the world is this booking at. They're all in San Diego. What a tsibble does that's different from a tibble is the kind of the first two rows at the top. It tells you 1 second, so you've got a periodicity that is kind of figured out for you. Since this isn't like yearly or monthly data, this is on a second interval, it's figured out that this is just 1 second data. And then it tells you what the key is as well. Something that you can do with tsibble, this is kind of the first function inside of it that's useful, is index by. Index by is kind of like a new way to group that says, instead of grouping by symbol or grouping by any other general thing you normally group with, this is kind of a time-based grouping. So it prepares your tsibble to do some kind of time-based summary action afterwards, like monthly or yearly summaries. So in this case, we've summarized by a 2-hour time period. So we've taken that last modified column and created a new column out of it, 2 hourly, that's in 2-hour chunks instead. And that's going to be useful because we can summarize by 2 hours after that. It essentially stores that information inside the tsibble going forward, so you don't have to specify it anywhere later. Other functions that know how to use this index by structure just use it automatically. And one of those is summarize. Summarize, like other dplyr workflows, allows you to kind of summarize some kind of result aggregate down to just 1 row per group. In this case, the groups are 2-hour time chunks. So in this case, we've taken a 2-hour median of the price, and summarized it down at the bottom. This is just a really nice workflow and a really nice, just like typable workflow that looks really good in my opinion. Also notice that Tsibble has updated itself and said, okay, I see this is not 1 second anymore, it's now 2 hours is the periodicity. The red is my own addition on top of the output just to kind of show you what the intervals are. You could do ceiling date instead of floor date. I didn't talk about how you actually calculate that new column, but essentially I'm using a function from Lubridate called floor date, and it lets you specify a column that you're going to floor the date of and then what period you're going to floor it to. Kind of the nice thing about index by is that it doesn't care about how you actually get that new index that you're going to perform the summary with. So it could be any function in there that maybe floors by year, or does anything crazy that you want it to. It just needs to return a new date column. So ceiling date, see at the bottom, instead of 14, which is the base of the interval, 16 is the top of the interval. The possibilities here are kind of endless. This is just a fun example that I came up with using ggAnimate that allows you to kind of index by 1 hour and then filter out some outliers and then put a map of this San Diego data by hour up really quickly. ggAnimate has these last 2 lines here at the bottom, which takes our new hourly column and transitions by it. Essentially, it creates hourly chunks of your data, plots each individual hourly chunk, and then combines them all together into a GIF, which is pretty nice. You can even use these current frame helpers, and that's how we get the title at the top that animates as well. I highly encourage you to check that package out, but that's not what this is about. The other interesting thing I was going to point out here is that blue is actually the most expensive prices of the booking, and for some strange reason, it's right here at 2 a.m. where a lot of people are buying $2,000 Airbnbs, and I don't know why. Someone could do some further analysis on that. So it's just one of the last things of the actual core Tsibble functionality is that it has it's really generic in terms of what kind of index it supports. So you saw POSIX-CT before, which is just date time in R essentially, but it also supports its own year-month type, year-quarter, hour, minute, second, which is another class that's out there. Nanotime, I think, is even another package that it supports, and then just generic numeric values. So if you just had 2013, 2014, 2015 as the index column, it would recognize that as an index just fine. Any questions? Yeah.
How quick is that function if you had a large data set and you're trying to summarize by a small time increment? I mean,
it's essentially still going to use the group by under the hood. It abstracts it away pretty far, but it's as fast as dplyr or C++ is, to be honest. So it's still CPP, and it'll be pretty fast. I haven't run into too many issues, but yeah, nanotime will slow it down a little bit if you're aggregating up to hourly or something, or minutely or whatever. Okay, so this is where we get into other Tsibble functions that I find really useful. These are some that I had a hand in kind of implementing that I really like if you've ever used furrr. How many people know what furrr is, the package? Okay. How many people know what the family of apply functions in R is? lapply, vapply, blah, blah. Good. So furrr is kind of the tidy equivalent of the lapply and apply functions in R that are consistent, and they have this extra syntax, and they're type stable, and there's all kinds of other reasons you might want to use them. But if you've got the idea of what lapply does in your head, you know what furrr does. These functions, slide, tile, and stretch, have these extra functionalities that rather than just iterating over something like map does, it allows you to iterate in a rolling way. So maybe I want to do a rolling mean, or that's what slide does, or tile does a mean over like individual time chunks, or stretch, instead of rolling and keeping a fixed size, it kind of expands and does your mean that way. To be a bit more explicit, slide will say, okay, I want to do the mean on rows 1 through 10, and then 2 through 11, and then 3 through 13, or 3, whatever. Tile will say 1 through 10, and then 11 through 20, and then 21 through 30. and then stretch will say 1 through 10, 1 through 11, 1 through 12, 1 through 13, and apply whatever function you've specified at that interval. I've stolen these GIFs from Eero. She's again created these with GG Animate, which I found really cool, but she gave me permission to use them. So we're going to do one example with slide. It'll be just sliding window calculations with overlapping observations. I love that GIF, so I use it. But we'll just go over one example just to not give you too much to worry about. But I encourage you to look at all those different versions of slide, tile, and stretch. Again, we're going to need some data, so we'll start with this Facebook data set. It's going to be pretty simple. You've got a date column that's daily, adjusted prices, and volume. And we'll just calculate some rolling averages. So that's what slide is good at, based on the description I gave you. So slide double, again, like other furrr functions, if you're used to that, you might see map double. That says I'm going to return a double vector or I'm going to fail. Slide by itself will always return a list, like map by itself will always return a list, just to be very type stable. The way you use this is by passing in a vector. Here we're passing in the adjusted stock prices. This could also be a list, it doesn't have to be a vector. And then it's something to iterate over, really. And then we're going to tell it the function that we want to apply at each chunk of data. Here, this is going to be the mean. We've used Perr's nice formula syntax to say, I'm going to do the mean of .x. And .x, because the size is 5, is just going to be these nice little chunks of 5 rows of the adjusted stock price. Does that make sense?
So is that the 5 is in terms of rows, right?
Yes, 5 would be in this case, it's really in terms of just like your vector, right? But in this case, it's you get 5 little slices of this adjusted column.
Right, right.
Okay?
What
Does that
if
make
you,
sense?
so it kind of assumes that you have, in a lot of cases, like equal spaced things, right? So like if you want to do like, for example, 5 days, right?
Mhm.
But you may not have an entry for all 5 days.
So I don't have that example on here, but I do have a way you can do that with nested, like tidier nest and stuff like that. So you can go ahead and nest by 5 days and then just do size equals like 1, and then it actually allows you to just iterate
Gotcha,
over
okay.
sections of 5 days. So it's possible.
Right.
I just don't have that example on here, but that was something I brought up with Eero about. And then the other example here is just the same idea where instead of 5 periods, it's 50 periods. Again, it's good that I really shouldn't say days because it's not always 5 days. That's not what it's doing by default. It's doing 5 like rows or 5 iterations of your thing. And then 50 as well. So essentially we've got short-term mean and long-term mean. You can just plot those and get a nice little chart out of it of your just simplest technical trading rules that you can imagine and run wild with what you can do with it. The important part is that it's very generic in what kind of functions that you can create rolling versions of. So at this point, you come back to the question, would it be nice to have just this tibble with time index support that just leverages these tools of the tidyverse very nicely? We've seen it be used with mutate, we've seen it be used with summarize, it works with group by. So at this point, you have something that's built on top of tibbles. It just learns about the index at creation, something that I really wanted, and then it's got this seamless integration with the tidyverse. So at this point, we now have this tibble that we've been waiting on, and it's open to build other things. So with that being said, there are some future plans that are in my head and that are in kind of a temp package somewhere that aren't completely ready for production at all. But it allows you to do some interesting things in terms of financial data. So we'll just start with this some mildly more complex version of the Facebook data we had before, where now there's multiple groups. Amazon, Facebook, Google, and Netflix are all in the same data frame. And I've just sliced the first 2 rows of each group so you can get a clear view of what's happening. We've already made it a symbol, we've already done our key and specified our index, and go ahead and group by symbol. What you can do with this in my ideal world is specify an index by, so index by year, telling Sybil, okay, I'm going to do some kind of yearly summarization or yearly calculation after this. And then you have a function like calculate return, which understands that like index by specification and allows you to go ahead and calculate yearly returns on whatever column or multiple columns you pass in. So I've told it to do calculate returns on the adjusted column, and it will go ahead and spit out adjusted return and append that onto your data set. It also changes the number of rows in your data set down to the actual yearly amount that you care about now, because again, you know, if this was daily returns, it would return the same number of rows, but in this case, it's yearly returns, so it's a lot less. It's only 12 if it was monthly returns in 1 year. What you can do with this is now, again, it's just a tibble, so you type it right into a mutate. You could do things like drawdown, calculate the drawdown of those returns over time, and cumulative returns, calculate the cumulative returns over time. The interesting thing is that fang time is grouped by symbol, so you just did that for all 4 stocks at once. And it's as extensible as you want in that you can do it for 500 at once if you felt like. Again, the symbol has updated to say, you know, this is 1 year now instead of 1 day. That is hopefully coming in the future. I think this is kind of like an element workflow. I just spent a lot of time thinking of how I can make that as easy as possible and extensible as possible.
Before you go on, can you go back maybe 2 slides?
Yeah. Which one?
Sorry, that was too far.
Sorry.
One more.
That one?
That one, yeah.
Yeah.
There's a transformation that happened on adjusted. Right, so I don't know if grain of data was like daily or something.
Yeah, it was daily.
Then it was like, I guess it's averaging it or taking the min or max or there's something that happens to the adjusted column that transforms it in some way, right?
So like just the adjusted column
Yes.
to calculate adjusted return, or I mean, this is just showing like for instance, this is Facebook. I don't know, 2013 1231 is the row that's returned. Before for Facebook, see the dates, they're different, if that's maybe what you're talking about.
I'm with you now.
Okay, so that's a good point. Like the other columns that come along with this different row tibble are the ones that match up with like this date. It's the end of the period by default, I think. So when you did floor date by year, then when you did that calculate return summary, it takes the end of the year, and that's the row that you get back along with that adjusted return. Because in my opinion, that makes sense, right? For adjusted return, you want to look at like it's looking backwards over the end of the year, so you're standing at the end of the year. So that's the row that you want to see. Does that make sense? Does that answer your question?
I'm with you now, yeah.
Okay. So that's all I have on Civil or tidyquant. Is there any questions right now while I'm at that? Okay. So switching gears to a pretty different question. Maybe we want to do cross-validation for time series. If you are familiar with the concept of cross-validation, it's essentially a way of taking all of your data that you're going to train on and saying, okay, I'm going to train on this 80%, hold out this 20% for out-of-sample predictions to see how well is my model doing. And you essentially just repeat that. I'm going to take a different 80% and predict on a different 20% and calculate some metric out of that. This allows you to calculate multiple metrics out of your one data set, and then you can average them together to get maybe a better estimate so that you didn't overfit. It also allows you to take confidence intervals because you have multiple resamples of that estimate, so you can kind of get a feel of how much does my model actually know versus did I just get lucky on that 120% that I did really well. And it keeps you honest a little bit. So the picture here I think does a pretty good explanation of what's going on. In terms of years, you could think about like this is the 2015 block, this is the 2016, 2017, 2018, 2019 block, and we've held out the pinkish ones. But then you actually start to think about it. And does this make any sense if that is years? That one in particular does not. I've trained on 2015, 2017, 2018, and 2019, and then I've tested backwards in time on whatever that one was in the middle. That doesn't make any sense, right? Like, how did I train on future data and then predict on past data? That's like breaking every wall everywhere. This one, on the other hand, makes a lot of sense. I've trained on past data and predict on future data. So in terms of cross-validation, machine learning and like other like non-finance-y, well, I shouldn't say machine learning, but other non-finance applications where the order doesn't matter can do this all day, and it's fine. But in time series and finance, the order matters, so you have to have different types of cross-validation. And that's where this comes in, cross-validation for time series. So we get these two types of time. It took people a second, didn't it? You get these two types of cross-validation, and I like this Uber article. This is where this picture came from. It's their introduction to forecasting. Get these two types of cross-validation. One is a sliding window, and one is an expanding window. The difference is really in the size of the training set and how that propagates throughout time. What you do in the sliding window is you start with maybe 50 data points, and I'm going to predict the next 20. And then you shift forward one day. This is still 50, this is still 20. Shift forward one day. And that allows you to retain the structure of saying, I'm going to train on the past, predict on the future in a nice way. Expanding window is just a little bit more, not even complicated, it's just different in the fact that I'm going to say 50 and 20, shift forward one day. Now it's 51 and 20, shift forward one day, 52 and 20. So it expands over time your training set rather than dropping things and keeping it a fixed size. This is nice if maybe you wanted to see, does my model ever run into the case where like at a certain sample size it becomes really stable and below that it's like not stable at all. It's a good way to kind of check your model against itself and see if it's the sample size that is actually what actually matters. Again, training size is fixed or varies. So the solution for like how you do this stuff, which is really important for time series in R, is to use rsample. Rsample is a package that has a lot of classes and functions in it to create and summarize these resampling objects. It allows you to do the bootstrap, it allows you to do cross-validation, which is kind of the first one I talked about, and then this sliding and expanding window. Out of curiosity, how many people have ever heard of rsample, the package? Good, all new stuff, okay, for most people. So rolling origin is the function in rsample that does both. And I have a little demo later that I'll show that really just goes through this in more detail. But rolling origin allows you to pass in a data frame. In this case, it's going to be just, again, a simple version of Facebook. It's not the data that matters, it's the functions. And we're going to start with an initial amount of rows that we want to train on. We're going to assess some amount, maybe it's going to be 20 rows, and then cumulative is what triggers sliding or expanding. Cumulative equals false means they're going to slide. So what this is going to do is take 500 rows to start with and predict on the next 20, and then 500 rows shifted forward one day, predict on the next 20, and so on all the way forward. And the way it does this is kind of by setting up those indexes of it's like 1 through 500 and then 501 through 520, and stores those all for you later to access. What you get back from a rolling origin object is this interesting looking nested kind of tibble, where this object is it's called a list column, if you've never heard of those. So ID in this case is the slice that you're currently working with. Based on the setup of having 1008 rows and the initial and assess that we did, we ended up with 489 slices of data that we're going to run models on. If you look at one of these individual splits, one of these individual slices, if you will, this is all that it actually returns. It says there's 500 rows in your training set, 20 rows in your test set, and 1008 rows total. If you want to actually rip out that underlying training data, those underlying 500 rows, you do that with the analysis function. You'll call analysis on a single one of these splits, and it pulls out the 500 rows that are useful for you to train on, and it pulls out, and then assessment pulls out the 20 rows that are useful for you to test on. So this is good later whenever you're actually running your models over all of these slices. So because it prevents you from doing any kind of look-ahead bias or anything, it's already separated out which rows are you going to train on and which rows are you going to test on.
So, and then you would just put Facebook splits index 1 inside of those?
So there's more elegant workflows than that, but yes, that is the idea.
Yeah, you can pipe it.
Yeah, so I'll show you here in a second how you do exactly that. Again, it comes back to using furrr to kind of iterate over this column. So this is the workflow for fitting these like multiple models. The best way to, or I'll start with describing just what the simple model is that we're going to fit. For each one of these splits, for each one of these sets of 500 rows, we're going to just do this simple AR1 model on the adjusted stock price. We're going to use forecast's ARIMA function to do this, and go ahead and tell it the order is 100, which corresponds to AR1. It's going to suck, but that's fine. We'll wrap it up into this fit ARIMA function. The best way to do this multiple model workflow is to have a function that takes in a single split object, runs the model on that object, and then outputs the model in the end. That's useful because then you can map over all of the splits and tell it to fit each individual split. That's how you can read that. What you get in the result is a new column model that holds all of those model objects. Each row is corresponding to like a set of 500 rows, and then the model that goes with those 500 rows. Does that make sense? Cool. So then what do you do, right? So I'll get into this into the demo, but a couple things that you can do now are predict on the assessment set. We haven't even touched that, right? We don't know how we did out of sample. We can visualize performance of that, calculate these out of sample metrics, and maybe even do some confidence intervals on those metrics because you have 489 resamples that all should be kind of calculating the same, maybe root mean squared error estimate or mean absolute percent error or something. So last before the demo, I wanted to show a little bit about furrr problem. You want to do this cross-validation with time series, but you want to do it faster. I just did 489 ARIMA models. That's bound to at least take some time, and it doesn't really take that long. R is fast enough, and that's fast enough that it really doesn't take that long. But imagine you had, I don't know, deep learning, neural net, whatever you want to throw in there that could take a much longer amount of time, and you're still doing this resampling type analysis. Maybe you'd like to do that in parallel on your computer, or furrr even allows you to do it in parallel on a cluster on AWS, or if you have a supercomputer, or if you have Slurm or any of that kind of stuff, you can do it in parallel there. So how does this work? Our sample and furrr just go really well together is something I was going to say. But how does this work? Rather than doing the map on the left, we replace it with future map on the right. Furrr is essentially everything from purrr parallelized. So each individual function in purrr has a parallel version. So now you just say future map, and you specify how you want to do the parallel processing. Multi-process is the way you tell furrr, I've got a parallel process using my local computer, just the cores on my local computer. So say my computer has like 4 cores, or I think mine has 2 physical cores, so the most I really expect as a speed up is 2x. And that says, okay, I want to use those. Future map will then split up all of those 489 splits into equal chunks and say, okay, I want each core of my computer to process a quarter of them if I have 4 cores. It does that all in parallel, returns the results, and instead of 8 seconds, it only did it in 4. But again, you can imagine the speed up if you had something much more complicated, and it's really like very little effort to make this happen for twice the speed. The cool thing, again, is that I won't ever show in this demo is that you can put in like plan cluster with some workers that are AWS in the cloud and run it in cloud instead, and it handles all of sending it up there and pulling the results back down, which is like mind-blowing. Any questions on that real quick?
So when you're doing the multi-process, you don't have to do any of the business about like registering your cores and all the stuff, like if you've had to do it in the...
So even cooler, besides just, if you like the underlying parallel package or whatever you might use, where it's like, I want to use like, I'm going to use this package over there in my cores, and I'm going to use this variable over there in my core. You don't have to export any of those. The underlying infrastructure that, to be fair, I did not build with not a friend of mine, but a guy I've worked with, his name's Henrik. He has built the underlying future package. That's why all these are prefixed with future. Has a package that essentially scans the code you've written and says, okay, what actually needs to be over there in all of those cores, and it exports them for you. So you don't have to do anything. Like, you don't have to set up how many cores you want. You don't have to set up any of the things that need to be over there. You just specify a feature map and everything happens for you. It's like black magic. And it works like 99% of the time. So the other 1%, I'm sorry. Write me an issue on GitHub. I'll see if I can help. Okay, so that's all I have in terms of slides. 38 minutes in. I think I'm good for a demo. Am I good for a demo?
You're good for a demo.
Okay. Let's see.
Hey, Davis, when we get to it in the code, can you
Yeah.
give us some intuition on like that .x syntax? with
Okay.
The squigglies, and I don't have it, so if you could just talk
Okay.
us through that.
When I get down to the section of it, I'll just see if I can go through it a little bit more. That sounds good. Let's see. Can you see that well? Is that good? Everybody? Got some nods? Okay.
Does per load future when you were showing that?
Furrr will automatically load future for you. That's like a hard dependency that I might be able to change, but I've talked to Hadley about that.
Is there a way to kill
The lights?
Yeah.
classes are just scratched up?
Should also mention while he's doing that. So the bit.ly link would have taken you to here on my GitHub. So if you Google Davis Vaughn and find the slides repo and then dig into it to the Charlotte R meetup, this README here at the bottom will show you, this will be a Speakerdeck link where you'll find all my slides already like posted online just through URL. And this is a, RStudio Cloud project. I was telling some people before, if you haven't used RStudio Cloud, this is what it looks like. It's in the browser. You can actually like clone my RStudio project that sits up there and have all of the dependencies that I used already installed for you if you just want to kind of play with this demo after the fact. You can get to that just by clicking that link right there, and then I think you might have to make a free account, but you should have no problem. Okay. So the purpose of this demo is to do these kind of like 5 things or so. We're going to use tidyquant to just get some stock data. I'll also show you a couple extra little functions in there. And then the main chunk is going to be on rsample, and then another little package that I'll just use a little bit that I've been working on called yardstick. Rsample for the cross-validation, again, would fit some type of ARIMA models, and then we'll see if we can do it faster with furrr. I just wanted to kind of show you what's happening a little bit more in the code and give you a chance to ask questions. These are all the dependencies and their corresponding versions. Some of them are development versions, so forgive me for that. So we'll load some of these here. And we'll go ahead and pull in Bank of America stock since 2001 with tidyquant. And here we go. So this is what gets returned from tidyquant. Like I said earlier, it's just a tibble with date, open, high, low, close, volume, and adjusted columns. You don't really have to care about this code. I just wanted to kind of visualize what the adjusted stock price looked like. 2008 was a great year, wasn't it? But this is Bank of America stock over some time. This is what we'll be working with. So a few quick tidyquant features. One that I didn't talk about but is very similar to tq mutate is tq transmute. Transmute is also a little known function in dplyr, but tq transmute has the special property, unlike dplyr functions, of being able to return a variable number of rows. This is useful again when you're changing periodicity like I talked about before. This is kind of the old way to do it in my opinion. You use something on a BAC here is like daily data, right? Maybe I want to apply a monthly function on there, and the function is standard deviation. Apply monthly is something from the XTS package. So again, this is the idea of taking our tibble, turning it into an XTS, applying some function over there that's XTS specific, and then getting our tibble back in the end. TQ transmute allows you to do that and return a different number of rows than went in. So if you were to run this, you were to get back the standard deviation of the adjusted prices and then all of the dates at the end of the month that corresponds to it. Does that make sense? The more flexible workflow, in my opinion, is to now use like tsibble objects and this index by summarize type workflow. You'll create a tsibble from your BAC data frame specifying that the index is date. There's really no key here because there weren't multiple stocks or anything, so we didn't have to worry about a key. This is what that returns. We'll index by 1 month, and you'll see that this is appended on a new month column, and you have these new this new groups line. This is the same groups line as what happens when you do a group by, but it's a little different in that you're grouping at a monthly periodicity. It's kind of how I read that. And this month column here on the right, actually, let me comment this one, that one. This monthly column here on the right uses the year month class from tsibble that allows you to kind of wrap things up in a nicer way when you really don't need the whole date. Now that you've done that and tsibble knows that you've grouped by this monthly periodicity, you can perform a summarize on that and get the results that you want in terms of a monthly calculation. Again, the summarize didn't know that it was monthly. The tsibble knew that you were doing something monthly, so you've kind of separated responsibilities. Summarize is more useful in my opinion than the tidyquant method because it's a little bit more explicit about what you're doing, but you also can do as many summary functions per month as you want to. Here we've done like the mean and the standard deviation rather than being forced to just do one thing at a time, the standard deviation. Does that kind of workflow make sense to people? I think it's very similar to the dplyr workflow, the tidyverse workflow that you might be familiar with already. So, now we can look at rsample's cross-validation type stuff in a little bit more detail. We'll start off with the sliding window idea. So roll the BAC data frame, if you took its number of rows divided by 2, it's about 2200. So we'll start with an initial size of our training set of about half of that, 2200, sorry. Start with about 2200 rows. And then we'll assess the next 50 and we'll say cumulative equals false, so it does the sliding window, stepping forward 1 period at a time. So you'll have a lot of models here, 2,181 data sets of them. But this is kind of the result that comes back when you do that kind of thing. And this is what you're saying, how do you access each individual like split? Is it like that, like, you know, bracket bracket 1 thing? Yes, that is how you do it. And you can look at a single split and it's very like misleading and like that's not fun. Like where's my data, right? So you have this single split object and it's like, okay, what do I do with this? Well, if I were to call analysis just on a single split, that should return my 2230 analysis type rows, and that's exactly what it does. So it says, okay, I saw your original data frame, but I saw that 2230 of these rows were specifically your training set. Here's what they are. Now go train on them. Assessment does the same thing, but for your 50 rows that are in your test set. Make sense? Step forward 1 day, and what do you get? So instead of the first rsplit object, we're going to look at the second one real quick, just to see the difference. So here was the first one. Again, note that we have 1, 2 as the first date here. We've stepped forward 1 day and dropped to the first day in our data set. So now it's 1, 3, but the size of the data set is still the same. This fixed size. Yes?
Is the second object in sliding splits anything worthwhile?
Okay, so that's what I was trying to say here. So splits is the list. Sorry?
Just tells you the slice name.
So okay, if you saw the thing that was indexed with bracket bracket 2, that's this column. Okay, so the splits column is then what you did bracket bracket 2 on. So you did bracket bracket 1 to get the first split, and then 2 to get the second split. Does that make sense? Yeah. So your second slice of training data. Okay. Jumping forward a little bit. Expanding window is just kind of the other one. We haven't seen an example of it yet. But by setting cumulative equal to, rather than dropping those rows, so it went from 012 to 013 as the first row, it'll keep expanding on that data set instead. I won't spend too much time on it, but I'll show you the difference here. This was the expanding splits. So you can see that it starts with 2,230 rows, the same as our sliding window, but then when you shift forward one day, it has 2,231 rows because it's kept that first original row and has continued to expand your data set instead. Just wanted to kind of like get a feel of what these objects look like. The last argument that is actually going to be a useful one for us in the rest of this analysis is skip. Skip is something that's in rolling origin that I haven't talked about yet, but it's useful for kind of like pruning back the number of like models that you're going to want to run. In this case, we had how many? 2,181 models that we'd have to run. That's a lot. And is it really that useful if we're just shifting forward one day at a time? Maybe not. So what skip allows you to do is say, okay, I'm going to take 2,200 rows, and then 50 rows are going to be held for assessment, and then I'm going to go ahead and shift all of that forward 50 days. And then take 2,200 rows and 50 days forward. So rather than just one period at a time, we just jump a big amount. It's not really like taking like random slices out of your data, but it's just controlled, so you have a lot less. So in this case, if you were to run this, you can see you only have 43 actual data chunks that you're going to be running models on instead. And whether the 2,181 would have gotten you better estimates of whatever that root mean squared error is, that's debatable. At what point does it become negligible? So much less data is much less intense in modeling. So you could see the difference there. Now we're finally to the point where we can fit the models, and this is where I'll kind of dig into like what is that formula, what the .x syntax look like, and what is it doing. So we'll load up some packages here that we're going to use. Instead of ARIMA, where we specified that it's an AR1 model, we're going to use auto ARIMA, and it's going to go ahead and specify our kind of like PDQ, our number of AR coefficients, MA coefficients, and differencing coefficients. It's going to go ahead and like figure these out for us. The interesting thing is that per set of 500 rows, it could choose different coefficients based on what it finds are the best for that set of data, which has interesting implications. So we're going to be using that skipped data set, so only 43 of them, so we're not here all day. And then we're going to create a function that is going to be applied to each individual split. So for each split, we're going to extract out the analysis set, those 500 rows that we're going to train on, and then we're going to run auto ARIMA on the adjusted stock price column. Again, you can switch this out at this point with whatever model you feel comfortable with. In this case, we're going to run auto ARIMA. And just to show an example, if you were just to run it on one of these splits, so like what does a split look like? It's just that. If you were just to run fit auto ARIMA on one of these things, it runs and throws back the ARIMA object that it found best. In this case, it picked ARIMA 111, one AR term, one moving average, and one differencing. So now at this point, we'll let it run for every split. I think it takes about like 20 or 25 seconds. So if anybody has a question, go ahead.
So we're fitting different ARIMA models to each of the 43 different time periods, right?
Yeah.
But at the end of the day, presumably what I want to use is an ARIMA model for like tomorrow, right?
Yeah.
Or next month or something.
Yeah.
So how do I kind of bring those two ideas together, if in fact they do have different coefficients?
Right. So for one thing, I mean, in theory, if if you think that like the recent past is more predictive, right, you use the most recent ARIMA model. On the other hand, you could say, okay, well, like last week's, or like the most recent ARIMA model said like I needed an MA5 term. Why did it say that all of a sudden? So this is going to be useful, as I'll show in just a second, in trying to determine like what is the most like parsimonious model for this kind of data. So real quick, I'll answer your question of how do you do this like map type stuff. Let's see. Okay, so here is, let me just kind of break out for a second and do its own code block. So this is what map does. So if you gave it like a vector, say it's just 1, 2, 3, it takes the first thing, 1, and that replaces .x in whatever function you've created. So in this case, it's going to be 1 plus 1 is 2, and then it's going to see that second thing and plug it in as .x and do 2 plus 1 is 3, and then the third thing is .x, 3 plus 1 is 4. That kind of makes sense? So just like whatever .x is replaced with the current element in your list or your vector as it kind of iterates over it. It's the same thing as doing like for I in 1 through 100, and then you did like object bracket I, like to extract out that ith element. That's kind of the same idea, except we've just replaced that in a nice format with just .x. Okay. That out of the way. So at this point we've kind of run all of our models. We've got all of our ARIMA models stuck in this model column, which is super nice. And now what do we do? So the first thing on here I had was like, what about coefficient stability over time? Broom, if you haven't heard of that, is a great package that takes essentially any model at this point and tidies up those coefficients in a way that kind of gives you back some kind of data frame or some kind of useful extraction from that model. In this case, if we were to look at sliding fits and we were to look at just this first little element here, this first ARIMA model, it might look like that. And you're like, well, how do I get into those AR and MA coefficients out of this thing? You could dig into it and whatnot and use dollar signs and brackets and everything you might need to. I think the coefficient function might work as well. But tidy just says, which is from Broom, okay, I'm going to go ahead and give it to you back in a data frame. I know what to do with this thing. Someone has written a method for tidy ARIMA, and it knows what to do with an ARIMA model. So we will go ahead and do the same idea of, for each model, I want to tidy it to get the coefficients out of that model. The warnings are fine, don't worry. And it will look something like that. So for each model, I have tidied it and gotten this data frame of its coefficients out of the model and stuck them in this coefficient column. Really, I want to see them. So the way you do that with these nested list columns to get that underlying data frame out for each row is to use unnest, which is from the tidier package, and you kind of unnest that coefficient column. If that doesn't make a whole lot of sense, that's okay. I didn't talk about that, so I'm sorry. But here is the result. You have the ID that kind of stuck around, which kind of identifies which coefficients go with each row. So the slice 1, that first model, we have an AR1 term and an MA1 term, and those are the estimates and the standard errors. It goes all the way down for the, 43 slices, I guess, that we have. And there's nothing saying, even though it looks like it here, that each one of these has to have AR1 and MA1. It could have had a lot more. So if you were to count them up, for example, you'll see that pretty much all of them had AR1 terms and MA1 terms, but a couple of them had, AR2, AR3, up to AR5 even, and some drift terms. But back to your question, it's like, well, what really matters, right? Like if it was the last model and it would have showed me you need an AR5 term, is that just like random noise from this like current model state, or did something actually happen And based on doing some kind of analysis like this, I'd say most